more path to that node in 2R rather than R. So if two nodes are in the same cluster after computing the zero extension, they are positive. And if the edges in the cut is a cut after computing a zero extension, put it negative. So correlation clustering was first introduced by machine learning guys like Nikhil Bansal, which is my favorite author. I like him very much. Avram Bloom. This is also my favorite researcher. Shuji Chawla. So they look at it as a global problem. They cared about global things. But you can also look at it as a local problem and care about local objectives more than global objectives. And in 2016, they wrote an article, Correlation Clustering and Bi-Clustering with Locally Bounded Errors. So the goal is to find a partition of V into an arbitrary number of clusters, S1, SL, that agrees with the edge labeling as much as possible. So you don't want the blue edges to cross the clusters, and you don't want two negative edges to be inside some clusters. Mathematically, you want to reduce the disagreement of that partition S, and for any vertex U, you want to you have a different disagreement. So U and V is an positive edge, but V is not in SI. By the way, you assume that U is in SI. And V is in SI such that U and V is a negative label, C of U and V. And it is an NP-hard problem in general, so we want to somehow approximate it. So, for example, a good objective could be minimum over all clusterings, S, maximum over all nodes. So the worst case, this is the worst case, because you want to maximize the disagreement over all edges, for all points, for all nodes U. And so we call this a min-max disagreement. But remember that this f function, which is a maximum function, if it is a maximum function, we call it min-max disagreement. If this f could be a summation function, we call it total disagreement. So f could be any function, but stick to one of them. For example, here in this article, we stick to min-max disagreement. And so the general case is that, the general formulation is that we want to minimize local disagreement. You call it f of d. Minimize over S, but local disagreement is the f of d function. For f could be maximum, for example. So it is proved that the natural LP and STP relaxation for min-max disagreement, if f is a maximum, then the natural LP and semi-definite programming relaxation for min-max disagreement have an integrality gap of n over 2. Remember, integrality gap is the m of integer, if it is integer, to m of fractional. And this is n over 2, it's too big. And integrality gap is always greater than 1. And they prove that min-max disagreement problem admits an order of root n approximation for general weighted graph, not just complete graphs, for general weighted graphs. So Moses Charikar introduced two different problems. One of them is a special case that is complete graph, but he also produced another algorithm for general graphs, which I will explain. So if should be the f function that I told you, we want to minimize overall s's, the maximum, for example, f is maximum. F should satisfy, first of all, if x is less than y, f of x should be less than f of y. If second, f of alpha x is less than alpha f of x. And third, f is convex. It's very important because if it is convex, then we can use linear programming. So we want to minimize f of d, and f is maximum, and d for any vertex is just c u and v, d of u and v, plus c u and v, 1 minus d u and v. And subject to, we have seen this several times, we use the triangular inequality, so it's one of our constraints. We want to look like a metric, and it is a metric. D of u greater than 0, d of u and v is between 1 and 0. So you solve LP and then you round it. You could round it deterministically. We could round it probabilistically, like we do in randomized rounding. An example of randomized rounding is CKR algorithm. So you round it, and for example here, the distance between u and v is 0.125, or another pair could be 244. But we want to round it, so to be either 1 or 0. So to round it, we don't use CKR algorithm. It is an optimum, maybe an optimum or tight bound for zero extension problem. But here, Moses Charikar invented a deterministic algorithm for rounding, which is very interesting because the proof of the theorems gives you some insightful ideas on how you can invent your own kind of mixed approaches, not very randomized rounding approach and not very deterministic, something between. And you can de-randomize your randomization algorithm. And okay, so since the integrality gap of n over 2 is big, lower bound of linear LP relaxation is not tight. So we use a different lower bound. Cmax, in that LP objective, you can. This is a maximum weight of an edge that is misclassified. So we can do some pre-processing, and then in this pre-processing, in phase 1, you can say that, okay, we compute the LP metric, but we have some additional constraint. We don't accept any heavy edge. So how can we do that? Okay, no problem. We can just put it in our constraints. So when you are solving that optimization problem, we just need to put it in the constraints. So for any edge u and v inside your positive edges, you just put it inside your constraint, no problem. So you see that the world is very simplified now, because we say we have almost omitted the problem because we have put it inside our constraint. And we say that, okay, this is the phase 1. And of course, by E plus heavy, I mean that all of the edges that your capacity is greater than C of maximum. You round it. So E minus heavy, it means that all of the edges, so this is in E plus, all of the edges in E minus such that CE is C max. So we do binary search until we get a good C max, because we then once we fix C max, then we are ready to go to the second phase, which is layered clustering, and it does the actual job of rounding. So what is phase 2 of this algorithm, which is called layered clustering? It means that assume that for the moment that there are some edges. So you have a very big long, you have a very long edge such that d of u and v is greater than 1 or 1 minus root of n. So this is a bad edge. Why it is a bad edge? Because it is inside a cluster, and also it is the distance is bigger than something that we have defined. So these are edges, as you see, the length of them looks very small. So it goes like this, and then like this. It goes to the next cluster after some time. So when you cluster this is a cut. So that's why this is a bad edge, because the red edge is inside the cluster. This is the another cut. This is a cut. So if output clustering does not separate them, then d of u and v is equal to 0. So you see why these are bad cases. This is a bad case because if you just write, you want to minimize f of d, and d of u is c of u and v, d of u and v, plus, of course, if e is in E plus CUV 1 minus D of U and V. And okay, so D of U and V is greater than 1 minus 1 over N. But if we don't care about, if output clustering does not separate them, then du of V, this becomes 0. And you're adding this to your LP value, which is bad. We want to reduce this. So in order to do that, we say that, okay, we are so let's say, let me clean this. I mean, what I mean by this is D of U and V. And so this part, the algorithm is designed, by construction, in such a way that no mistake is allowed. No mistake is allowed. And here, mistakes is allowed. Mistakes is allowed. Why? Because these are the points that these are the edges that d of u and v is less than 1 over root n, and because this factor is small, then we don't whatever this c is, the multiplication is small. So it has a small contribution to the LP value. That is nice. We have somehow heuristically tried to reduce the LP value, which is a good thing. And that's why I like the idea of Moses-Charikar. Another example, which is a bad case, is that here, for example, you have a blue edge here, for example, you have a blue edge very small, very, very small. The distance between them is d of u of v is less than 1 over n. And then the other distances are big, for example. Extreme cases. And this is very small edge. And it is this edge E is in E plus bad. It means that first of all, the distance is small. Second of all, it crosses the clusters, but it is blue edge. I mean, it is a positive edge, but it's crossing, so it's bad. So for these two reasons, we call it bad. And as I said, we want so we design algorithm so that it ensures no mistakes are allowed, are made for edges in E minus bad. However, we let it to make mistakes on edges which is E plus bad. So we consider the auxiliary graph G plus of bad, which is of all vertices, but the edges are, it has all vertices, remember? But only the edges are included only if they are inside E bad. And we equip it with the shortest path metric such that L of E plus bad to 0 and 1, we round it, we are trying to round it. So L of E, by definition, we say that it is 0 if E is E0. 0, it means the distance between them is just 0. And if E is inside E plus bad, but doesn't have E0 plus, then it is 1. So this is the length that we describe. So an example of this is like going from SI to TI, U, SI, V, and TI, for example, is here. This is a connected component. This is another connected component. So this is X, this is X prime, other connected component. So in each connected component, we do some algorithm. So we examine the layered distances between SI. We always start with SI to any point. And this defines and performs a carefully chosen level cut. For example, if it is bigger than something, round it to what? So it ensures no mistakes. So a rounding mechanism is somehow, it doesn't allow mistakes that are made in edges E minus, and number of misclassified edges is almost order of root of n. So the last thing I want to say is the algorithm. And the algorithm is like this. First, it is empty, and then you let D to be LP solution. With additional constraint, you solve the LP with the additional constraint. As I said, it is 0 if E is a heavy edge, and D of U and V is 1 if E is a heavy edge but is negative. And then while X contains SI and TI, you distance between SI and TI, you define some L here that Lij, this is important, that this is all the U, that the distance between that SI that I said and U is J. So, for example, we choose J star less than root of n minus 1 over 2, such that, so the algorithm is this, such that Lj star I and Lj plus 1 star I and L J star